There we go. Okay, so we'll pick up with the last little bit we had to do. Let me just do a real quick recap of these. Well, actually, next week we'll talk about art and that a little bit more again. But it is helpful to see this actually a couple times, because if anything confuses people, it's attempting to do art. And it's actually it's a simple idea, but you have to get used to switching from a geometric understanding of the world to an algebraic area. If you get used to that, it'll help you tremendously. As engineers, this is a skill we have to draw a lot of. But it turns out a lot of times graphically, it's the best way to understand an algorithm, where algebraically is usually the best way to implement the algorithm. So anyway, so let's just recap the idea. We have, we're trying to solve a linear equation. AX equals B. A is a big old matrix. B is a vector. X is a vector of unknowns. So A times X is a vector the same size as B. We're going to make an initial guess X0. In this case, I'm making it a 2-by vector so I can draw it. Each of these green lines is one row. So it's a row out of A and the corresponding element in B. So that A row times X will equal B if it's on the line. Right? So technically, if it's closer to the origin, the result will be negative. And if it's further from the origin, the result will be positive. So you can even tell how far off you are. You'll get a distance measure of how wrong you are from that. But we're not going to worry about that one for the moment. Right? So just content, we've got these lines. These lines are defined by a row of A times X minus B. And we want 0. And that's what the locus of green lines for each row. So we take our initial guess. Where all of these come together is the solution. If there is a solution, they all come together at a point. If they don't all come together at a point, there is no solution. There are some times where they get really close, like my bad drawing doesn't actually get these perfectly lined up because for some reason, Microsoft put their snaps such that I can't snap them all to the same point. Thank you, Microsoft. Very cool. So, I got as close as I can. In reality, errors are going to make it not exactly get perfectly right. And what you'll get is you'll get a little shape if you were to zoom in on it. And in real life, the errors on B will perturb it. So you'll get like a little region. And it'll actually bounce around the outside of that little polytope, because there is no actual solution when you get to that small. But usually that's so tiny it doesn't matter. But if it's really big or the equations are really inconsistent, that's a bigger problem. But anyway, what happens, we take our guess, we're going to project it on one of them. That's going to give me my new guess. We're going to do the same thing through each of them. Now, different orders will give you different convergence routes. However, if you notice, as long as I go through all of them, I am going to get closer and closer towards that center. Let me ask you a question. Where do you see the biggest gains?
Like the first couple guesses, like biggest gains isn't like getting closer and closer.
Okay, that seems to do pretty good. Where is the biggest single improvement anyway? Anywhere between what two, in terms of getting, a big difference between two successive xi and xi plus 1.
Either 2 to 3 or 3 to 4.
Yeah, those are both pretty big changes, aren't they? Right? And what do you notice about the difference between those two?
The changes orthogonal.
Yeah, the closer you get to orthogonal, the next vector, right, the best you're going to do. Imagine if I took one that was truly orthogonal. Well, if it was truly orthogonal, you jump right to the center of that whole area. Now, In higher dimensional space, that's not actually true because you have more, this is because there's 2 dimensions. So when you do to the next one, you're knocking a dimension out. But in theory, if you have a truly orthogonal position, it will do that. Now, noise will cause you some issues on that a little bit, but in general, you don't want small angles. It would not be a good update if it's a really tiny angle between them. In general, you want them to be a little bit larger. So if they're too small, right, you got a problem. If they're too big, you become highly dependent on how correctly you wrote the equations. So any uncertainty in your modeling causes you errors, right? So noise causes you errors when you're too small, modeling problems when you're too big. So somewhere in between means you're kind of maximum robustness between the two of them, which means a 45 degree is pretty good. We usually aim for a little bit less of that for a lot of our updates, usually somewhere in the 30s. But it's still somewhere in that area, say 30 to 50 is a really good update, typically. Because it avoids the 2 type of errors that come into your equations. So that's art. Take each one in turn, one at a time. Obviously not parallel, but all updates get the benefit of all previous updates, even if it's partway through the sequence. So that makes it really fast. So this is what makes art, in some sense, the holy grail. It takes advantage of all previous updates. In parallel ones, obviously they can't take advantage of their neighbors, right? So you see Chimino is the exact opposite. This one is, that one was fully sequential. This one is fully simultaneous. We do the same projection on each one of the lines. We have that polytope of all possibilities. We just take the corners. Anything inside the lightly shaded blue region is some weighted sum, right? If you think of each of those as x0, A, B, C, D, E, F, or whatever, right? A weighted sum of all those where the weights add up to 1 will give you that polytope region. So then you're just kind of picking it. If you pick it, I think there were 6 of these, but I don't remember off the top of my head, whatever, the 5, 6, whatever it happens to be, right? If you did 1 over the number of rows, that would in theory give you the dead center right there, right? That's the average. So that's kind of, most people usually pick the average, although there are a couple other schemes that are out there. Then there's some, what if I do hybrids, right? What if I took, a shorter set of strings? So I take those 2 green ones. So I think I did pick 6 of these. I think that's so I could split them up like this. So I pick 2 of these, and I get to that point. And I pick another 2, right, different than the first. I left the first one in there just kind of shaded in the background. And you can see the next string, and I pick the last 2 and do them in turn. Right? So now I've got those 3 different points. If I do a Chimino style integration, right, so I kind of did little strings of art, and then I combine them together like Chimino did. I've got 3 endpoints, so I take the weighted polytope of those 3. You can see I do a pretty good job, right? So those are strings. We call each one of these, we strung together a couple projections, so they're strings. And they kind of look like a string too, right? Kind of dangling to the endpoints. And then they're averaged to get my final projection. So this is a string average projection. The name really tells you the algorithm. Believe it or not, if you know these pictures, you can write the equations right from the pictures. So that's why I'm trying to make sure you get the pictures down. Block iterative. I mentioned this one's really good for GPUs because in general, what it does is it now breaks it. I pick 3, you can see the dotted lines, and I do a Chimino style. Now, if in reality I've got like billions of these histories, I'm going to have, say, 10,000 of these blocks. Well, 10,000 simultaneous projections is like right up a GPU's alley. It's a size it can handle. It's not going to be really great at a billion, but 10,000, 40,000, GPUs love that size, right? There's lots of independent, it's projections, GPUs love projections, right? That's the exact type of math they were built for because that's mapping textures as a projection. So this is exactly what they were built for. And we get a whole bunch of them. We did 3 here, but I mean, I literally imagine it's 40,000, right? And I throw it onto a GPU that has like 2,000 of these things, right? 20 cycles later, it has done this first thing. And that's like a tiny, tiny fraction of a second. And I can have different GPUs have different sets of these, right? Or even have in memory and just load them in and out, and I process through one for a fraction of a second, slam the other one into cache, and then process that one. So you can kind of see the advantage. I do Chimino, but now what I'm going to do is for my Chimino update, I'm going to do kind of string Chimino updates. So instead of, this is kind of like an art of Chiminos. And the previous one was a Chimino of art strings. So it's really just which way do you break them. We always do those same two basic maneuvers. You can see I take the previous one, I grab the ones I hadn't done yet, and I do that. So if I was doing this on a GPU, it would be like 40,000 at a time until I get my way up to 1 billion. I'm done. I can repeat that as many times as I want, and you notice it does a nice job moving ahead. The challenge with the strings is each string is sequential inside, right? So I have to load all of the different portions of the strings, so that's not as amenable to a GPU, which really wants the parallelism up front. Whereas with strings, it puts the sequentialism inside. Now that type of sequentialism inside is great for a CPU. So if I have a cluster of CPUs, each CPU gets a few strings. CPUs love to do a sequence of operations, right? They got a few cores, you give them several strings to handle each, they're happy as a clam, they communicate their results to whoever else is the head. And so string average is great for a traditional cluster, right? This kind of block iterative is really good for GPUs. But this is why I say this is where your hardware becomes, non-trivial on choosing your algorithm. Really, you can't choose a good performance algorithm without understanding the hardware. And that's more what I kind of want you guys, particularly as engineers, to understand. How does the hardware and the software interact? Does it make sense why each of those algorithms does? So which one is going to have, what type of machine would you have to have an advantage with, let's say, art?
Probably CPU type.
Yeah, and a single CPU, a single core, right? How about Chimino? Yeah, GPU if it's big enough to hold it. If it gets too big, it'll just kind of get ugly and way down. So that's why at that point you want to kind of bring it in chunks, things of that sort. So, yeah. Anyway, that's the ideas, right? So if you look at those and see, okay, how is the parallelism done? That's where you want to figure them out. Okay, let's talk about BIP. So what I want to do is imagine here for a sec, I'm just going to break it down. Imagine there was just 2 projections in BIP. Right? We had 3 it was projected on. So this is just 2, and it just makes it easier for me to draw the graph, and I can show the weighted options between them. Right? So I've got a previous one, xk, and I'm going to project to each of these. And this is my weighted average line between them. Does that make sense? Okay. I'm going to show you the equation. And what we're going to do is we're going to figure out graphically how do we get the equation. That make sense? All right. So I'm going from xk to xk plus 1. So what that's telling you is I'm getting some delta between them. So we're writing xk plus 1 as something, this little projection update, plus xk. So xk plus 1 is xk plus something. This whole big thing in here is technically the distance between those 2 points, because that's what delta is. Does that make sense? Okay, so let's figure out why these things add up to that. Now, let's see if I did this right. It should color animate for me. There we go. Okay, so let's grab the first one. What is a projection? Anybody remember projections? Have you seen projections in matrices? Anybody taken linear algebra before? Yes? Did they do projections? please?
They did, I'm just. it's a little-
Trying to remember. Okay, so that's cool. It's a different way you have to explain it if people have seen it versus not seen it. If you haven't seen it in a while, you've completely forgotten the whole thing and could never write it down. However, when I mention ideas, it'll come back to you. If you've never seen the ideas, I have to explain and prove the ideas. So that's what I'm trying to establish. Okay, so imagine for a sec I'm doing a projection. Projections, think of a projection like a shadow, right? So I got my arm up here, and imagine I'm trying to get the projection of my arm onto the ground. And I'd have to have a single light source to be able to see it, but you can kind of imagine when it's coming down. And if my elbow was somehow on the ground, but you could still see it, right? Or maybe on the top of this monitor, right? The projection coming straight down, if the light's straight above me, right? If we describe this top of the monitor as A, right? We would expect a couple behaviors, right? The projection of A onto A, right? Should be, that's something laying on the top onto itself, right? The shadow of the shadow should be itself. It shouldn't change any, right? What we're going to do then is we're going to take a look at how similar they are, right? What's the angle between them? Remember, we get the cosine of the angle by doing the inner product, maybe called dot product. So to mathematicians, they write the inner product using these angle brackets, right? So this means the inner product of the ith row of A with xk. So xk is this, and this line here, let's say for instance, is defined by the ith row. Okay? So AIXK, that's determining the inner product of those two. The difference between that and B is this green line. It's 0 if you're on this green line. Right? But I'm not on this green line, I'm over here. So I'm on the 0 side, so it's going to be negative, but who cares, right? We don't necessarily worry about it. It's just, it's off. And this distance here is how much it's off. Right? Basically. But there's a little bit of a caveat to this, right? So that is the equation of this line, and it does give you some relative indicator of how far off it is. But A is a vector kind of defining, think of it as like defining the slope. But if I took, let's say my slope was 1/2. Is there any other way I can write 1/2? 2/4, right? That's legal, isn't it? But that means 2 in y, right, and 4 in my x direction. But that's going to mean the scaling will be a little bit different than here. Right? So based on how I picked that A, that's the M, right? So I could have picked 2/4, I could have picked 3/6, I could have picked all kinds of stuff. Right? If A has different scalings, it's not unit length. It's going to skew the distance. I got to remove A's messing up my distance. All right? Now, in addition to it, I've got to have, this is just giving me a size. So if I divide it by the norm of A, not the norm of A squared, just the norm of A, then I've got a distance from this line. Does that make sense? But now I need a direction too. What is the direction of this arrow? Well, that arrow has to be, when I do my projection, what do we say typically about our usual projection? We want what type of projections? Orthogonal, which tells me where's the orthogonal point? Down here. This has to be 90 degrees. Right? So how do I get a vector pointing 90 degrees to that line? I could, but I don't need to. So this relies on an interesting observation about lines. Right? Any of you ever had to deal with lines in higher dimensions? Most people hate them in some sense, right? Because people go, oh my gosh, right? Y = mx plus b, nice, that's ugly as heck. Right? And so people rapidly start hating it. And it's because they taught you lines correctly, but in a non-extendable way. Right? When they gave you y equals mx plus b, it's correct, but how do you go to the next dimension? Right? There's no easy way to go to that next dimension. What you actually have to do is what physics does. And this is one of those reasons why they probably did this in your second physics class, but they might have done it in your first. You ever see where they deal with like a shell and they have the flux and there's a normal vector and all that? Why do they deal with all that kinds of weird stuff like normal vectors and things like that? Because the normal vector defines that shell. The normal vector actually defines your line. Here's a line, right? We think of it, right? Here's y, here's x, and we've got, right, some delta x, delta y, right? That's on here. If I wanted to write this, then we would just say the equation for this line, it's got some offset b here, right? So we've got that y equals delta y over delta x times x plus b, right? That's what we're used to. Y equals mx plus b. However, this is not the best way to write this. Consider for a sec this line, and what if I had a normal vector? Anybody know the equation for a vector 90 degrees off? It's not as horrible as it sounds. Right? This one's going up, so this one is going to have negative, right? Because we always kind of go that direction, right? We always go left to right. So it's going to be minus. And then if this is a 90 degree here, that means that is, so that means this angle is that angle. So these two triangles are the same triangle. So that has to be delta y. That's the only confusing thing is it flops. And this is delta x. Huh?
Isn't that just like multiplied by a rotation?
Yeah, so here's the neat thing is you can rewrite this whole equation. If I, instead of writing xy this way, I write xy this way. Right? And then I took its inner product with this normal vector, which its x direction is delta y, and its y direction is minus delta x. And then we know that this inner product is equal to the offset from the origin there. So that times that equals b. That's a line. The neat thing is that extends to as many dimensions as you want. You go to 3 dimensions, I'm just going to have 2 orthogonal vectors, so I'll have 2 of these equations. Right? But the x and the y stay the same, so you just get a matrix now. You can now extend and have lines in however many dimensions you want. That extends as big as you want. And if you think of it in that terms, it's actually a pretty nice way to go, right? Well, the way you define a line then is by this normal vector. So this is kind of an ax equals b. Or in particular, just a row of it, so maybe like ai equals bi would be a good way to describe that. So if I wanted a vector that was orthogonal to my x, my line, what would it be? It's just the row of a that made it. That's what you're actually specifying in the row of A. You're specifying the normal vectors. The path that it travels through defines the normal vector for those green lines. And those distances B are actually the measure of the distance off the line. So it's from the origin to that line along that line perpendicular to it. So literally speaking, if you were to take this one that we're looking at here, its orthogonal vector would go like this. Right? That distance from here to here is the value in your B. So the AI is the orthogonal vector part, and that defines a line. Anything perpendicular to that point, right, carried out is going to be equal to 0 for offset purposes. So this has to be orthogonal, so it's AI. That's why it's AI, right? So it's kind of a fun thing. The direction orthogonal, so that's the orthogonal direction. This is the distance, but I've got now 2 AIs in here, and they could be scaled weird, right? Because it's just the slope. It could be 1/2, it could be 2/4, 3/6. So you better divide by the length so it's normalized. That's all you're saying. So this is a really fancy way, right here, of just saying this little red circle line. And there's 2 of them, because we have, in this particular case, we have 2 of the AIs in here, so the summation is over those 2. So it makes sense why this is this little components. And now you can see it's perfectly an orthogonal projection, yay. So you can look at the equation now and tell it. Whenever you see, you'll see these all the time in there. That's all it's doing. That's defining, you'll hear people call this the hyperplane, because it's a line, but when you're going from 2 dimensions, a hyperplane is 1 dimension less. So from 2 dimensions, my plane, the hyperplane is a line. If I was in 3 dimensions, a hyperplane would be a surface, yeah, what we consider a regular plane, right? If I go to 4 dimensions, it's a 3-dimensional space somewhere offset from the origin, so on and so forth. Okay, now we do a weighted sum. So we took those 2, each of these, they got a weight, say half. So I multiplied each by, say, half, and then I added them together. I get this middle one. So that's all that summation is doing. Looks fancy as heck, but all this says is I'm selecting some subgroup. Like all this fancy notation, this just means I took your original set of rows and I broke them up into m different groups. Right? So if you had 5 things and or 10 things, I broke them into 5 groups. I could have 1, 2 here, 3, 4 here. It's nothing fancier than that. It's just saying break your thing up into groups. You would normally pick these groups so it fits nicely inside of your GPU for memory purposes. And you just pick it for memory reasons. And then, but you have to remember to do all of them. Intersect them, don't leave some out. Otherwise you lost data. And this is just saying I have to go through all of them, right? That's 1 full cycle, right? I've got to walk through each one in turn. And each of my, in the subsidiary, these weights have to add up to 1. So inside a block, if I'm in block 1, the weights in block 1 have to add up to 1. The weights in block 2 have to add up to 1. Because otherwise, I'm throwing data out again. So that's all this is saying. Make sense? Yeah.
Is there any reason in practice why the weight vector wouldn't be uniform?
Why
The weight vector wouldn't be uniform?
let's say, for instance, you had something you knew was definitely noisier.
Okay.
That would be why you would have something different. There are some times when like a particular sensor isn't calibrated as well, so maybe you have to do something on that. Over time, you might sometimes also notice that that particular measurement is a little less consistent. So there are ways you could start trying to estimate errors. We won't here, but you could try to estimate how big is the update, and sometimes one just is like really out there all the time. So you go, oh, that's an outlier. Right. Even if it wasn't miscalibrated, something wacky happened there. So therefore, we're going to downgrade it. In general, you would absolutely just pick them as the weighted average. Delta, if you get more information, take advantage of it. Right. But yeah, that's the big reason. Okay, so far so good? But we're not there. We're down to this little bit here. So that's that last little lambda. Remember our lambda, we said we sometimes only take a fraction of it because it lets us take the inside root. We could actually, in certain cases, also overestimate if we happen to know it's going to do a very small job. If you saw with pure Chimino actually often when you're adding all of them up over like a million, right? It doesn't do a very big change. So sometimes actually with pure Chimino, you make lambda bigger than 1 so that it makes up for that innate scaling that goes on by averaging all these things in a whole giant cloud. But for pretty much everybody else, it's always less than 1. So that's all I've done here. So this is the weighted line reduced down, right? But the reduction from here to here, so that over this is the value of lambda. And so that's all this is showing. Once I've incorporated the lambda, it takes something short. That is your full equation. So see what I'm saying? If you understand what the picture looks like, that looks like a crazy complicated equation. But once you know what it means, you know, this is just a book definition of a projection, weighted average them up, do it over all the ones in your set, and pick some lambda less than 1 to scale it because it'll converge faster. You know, don't be too aggressive, it's not as quick. Okay, then you add in the x, k, and that gives you the new xk plus 1. All right, just a couple notes on calculations. So when you do the calculation of b minus a times x to get the residual, that's that top of it. Notice how it's kind of, your data ends up, your data is blocked into rows. So that's what I tried to do with the yellow things. That's kind of like how you blocked them row-wise. So that's how the memory is separated. So when you go to calculate b minus a, you actually have to read across all those memory blocks. All right, that's what this is really pointing out. And that r, the net residual from there, you only care for your particular estimate up here, right? So you can still separate those out, but you're implicitly going that way. When you do the update, the a that you're using is actually a vector in a direction. So now, you know, the AI has technically been transposed. So it was this way, now it's that way to update x. The second you've done it, you've flipped it. And now your residual vector's there, and it's that times that residual vector. That's the update for in the projection matrix. Remember, it's the the residual vector times the AI normalized length. And that gives me my update to x. So if you notice, the reason I'm blocking it in row-wise there, technically it's row-wise here, but since I had to transpose it, it's kind of column-wise. So when you're reading your memory, you're either reading row-wise or column-wise. But if you're familiar with memory, if you remember from when you did machine org and all that, computers tend to like to read row-wise or column-wise. They don't like to do either because they set their cache up to look in advance. And they either do a row read, and so they do row memories of updates or otherwise. So this is just a note. You will get bad cache performance with the following delta. You can get the best you can, like let's say for instance, I'm doing row reads on here. If I set this length here to be some multiple of your cache's stride length, it'll at least correspond to your stride length. So it's a little better in cache performance when you do that. And that's why I want you just to realize transposing matrices always affects memory performance. And so you just want to think of, in terms of cache, how do I make sure I minimize the problems off of it, right? So when you think about the blocks, don't just think about the blocks in terms of what fits inside my machine. You want to have a secondary thing that checks, is it also proportional to my cache stride length if I'm doing row or column wise? And if you were doing the other direction, if you were doing column direction over here, you'd want to set it for the column stride. So it basically works out the same for either. So if you kind of think of square blocks for how the cache is going to load, one stride, you know, keep them in nice, so those gridded squares fits nicely inside these rectangles. If you do, good performance. If it goes over, you get these cache misses all over the edges, and it just gets ugly at that point. Cache misses are always slow. One final thing, when you sum up the inner product, right? So you do all these kind of inner products and calculate them, and you have to add them together. Normally we go multiplication is ugly, and who cares about addition because addition is fast, right? Not true once you get to vectored machines, right? Because I'm doing the multiplications in parallel, but the addition has to be done in serial. That's what slows it down, right? It's not that addition is bad. It's that the addition operation in this case is a reduction operator. You're adding up a bunch of independent calculations to a single value. So I need all of them done. So what we want to do, this is actually the best way to do it, right? Because it takes a lot of things in common. So what we're gonna do, I technically just wanna add them all up. And our first inclination is to walk down the thing and add them up. But if you do, that takes n operations. This plus this, and then that plus that, right? It would go down off the edge of the screen. So there's a lot of different ways. So some people go, well, what if I just do add these two in parallel, so on and so forth, right? That's often what the next guess people do, right? Add 0 and 1, add 2 and 3, add 4 and 5. You get those in the next level. But 0 and 1 goes here, 2 and 3 goes here, 4 and 5 goes here. See the problem? They're spread across, and you've got a gap in between. So when it loads into cache, that gap loads into cache, and it doesn't fit in cache. And we're not just doing 16 things here, we're doing 40,000 plus, right? And your cache stride now really matters. So if you do it this way, 0 plus halfway across, 1 plus halfway across plus 1, so on and so forth. They all compress to the lower half, minimizes cache use. So all those adds are in parallel, and the result is densely packed. Follow the same procedure for the next one. This plus halfway across, plus halfway plus 1, right? Condenses down. It does them all of those additions in parallel, but again, it's compressed, so it maximizes your cache performance. And you just keep following that procedure. If you do that, it takes both advantage of the parallelism inside your machine, and it minimizes cache memory, which is always a performance addition for us. Does that make sense? So I mention this because I don't think too many people would have thought this as the first way to sum up those numbers. But if you look at this, this is a true log-based 2 with no memory penalties. If you just do the 0, 1, and 2, 3, and 4, 5, and that thing, you'll get a log-based 2, but you'll have memory penalties the entire way. Right? Memory penalties are usually some reasonable fraction of a second, right? So it's probably going to cause a multiple of at least 10 to 20 times onto your performance of the thing, right? The order of magnitude or worse difference. You know, if you did in sequence, you're in the worst of all lands, right? You know, it just slows everything down the heck. So anyway, this is kind of my note as sum carefully. Okay, so let's take a quick look how this works, right? I made the comment to you that, you know, we want usually 20, 50, 100 time voxels. So the way we came to that conclusion, we took a good guess that it should be somewhere in that zone, but then we don't take our guess, we do experiments and check and see. So this was 1 proton equals 1 voxel. A was a square matrix. You know, all this was generated from a phantom. We made the phantom up. We know the phantom exactly. We generated the histories from it. It just depends how many histories with noise appropriate to nuclear scattering noise. So, you know, if I just had 1 per voxel, if I had 5 per voxel, see how much better it's getting? But you can still see in the background, it's still really pretty noisy. This is 10 protons per voxel on average. Right? Now you don't actually pick 10 per voxel. You just go, oh, I've got 1,000 voxels, so I'm gonna make 10,000. I'm gonna spread them as evenly as I can, and you hope for the best. So I can't guarantee they'll be exactly 10 per voxel. You know, that's why it's a little bit of stats on here, but you know, at 10 per voxel across the whole thing, it's gonna be fairly even. bigger the stats that you've got in here, the more it's going to converge to it. But you can still see the boundaries. There's still some kind of noise, and the background particularly not exactly the nicest. If you look inside, you know, these particular areas basically designed to be somewhat like vesicles. You can see there's a lot of noise in the background on them. By the time I get to 20, it's pretty good. If you zoomed in, you'd still see there's still some background. I didn't show more than this because I just felt it was kind of getting too much. At 50, it looks really good. Right? But in general, by 50, and this is pure simulated data, you figure real data is worse, so we just doubled the number again. We said for real data, you know, it's beautiful at 50 here, it'll be pretty beautiful at 100 there. So that's basically how that number came in. This is a cross section through to show you what each one did. So you can see the real one is the dark blue. The light blue or cyan is the first one. You can see it's really choppy. But notice there is still, you can see the edges are definitely brighter than the centers on the blue. There are some areas where it goes down. You can see a little bit of a slightly darker zones. That's not pretty, but you know, when you're looking here in the line profile, you go, oh yeah, it does kind of go down, doesn't it? Right? It does go down a little bit. It's not beautiful, but you can tell. Look by the time we go to the next one, right? By the time we go up to the 5, the 10, and then the purple, you can see which magenta, it's really falling at time. Yeah, that's at the 20. So, you know, it gives you an idea. So this gives us a pretty nice indicator also that the values in here are correct. Right, because you can see these here are going pretty close to that dark blue line, which is what I want them to be. And you can see as they're coming in, the magenta line is getting closer and closer to the corner. But it would only hit that at infinity. Right? Otherwise, it's Gibbs phenomena taking you out. Okay. Just some more examples. They're on here. These are different relaxation parameters in the reconstruction. And you can see the relaxation parameters. There are some differences. This is a small one. So given the small history set and size, it'll show you it's going to want, for SAP, in this particular case, a slightly higher number. Right? The relaxation parameter will depend on your one. If we were to go up to, this is like 20,000, when we get to the millions, basically if you go up in order of magnitude, you want a 1 over order of magnitude, roughly speaking, on the others. So by the time we get up to hundreds of millions to billions, you're shifting that over 2 or 3 places to account for. But again, we do the same exact thing to test our relaxation parameters. This one just gives you final, RSP. What was it? What should it be? So you can see, what was the actual mean RSP and what did we guess when we were going through. You can see it's really darn close. Given that the original system is going to be 1 to 5% off if you did X-rays, the improvement is noticeable, and for less radiation. Okay. This just gets into the phantoms. So these are the phantoms we're using. One's a Sears head. It's a company, and they basically, this one is a pediatric, and it is actually based off a 5-year-old skull. So they make their version of it, but it's, based off an actual pediatric skull measured and duplicate as close as they can in materials and everything, and then overlaid in plastic. And this just gets into smart once we did those phantoms. I'm not going to go too far into that. But anyway, that's essentially what we've got for ours. So we can see how we pick those parameters. Do we feel good with that? Okay. I'm going to go into how do we do things with FBP. And remember, I can do FBP also for the ion CT. I just have to do it along those curved paths. So FBP, we normally do straight lines. We can calculate the MLP, do it back along the MLP. Boom, FBP version. Okay, so let's try to remember, has everybody seen FBP before? You may yes, you may no. Okay, some yes, some no. Okay, here we go. Imagine I've got this, right? So this is obviously meant to be some cross section. This is from the book. So I tried to use their pictures to correlate to your readings as much as possible. The book is actually a pretty good book overall. So I do encourage reading their stuff. But imagine this is kind of like some chest cross section for whatever reason for a person. That's all they're trying to show here, right? Skin and internal organs and whatever. All right. This is my detectors right here. And it's rotating around me, right? So at this particular instance that's taking a picture, it's at angle theta, right? And later on it'll rotate. There's a source, and we're just going to consider generation 1 for the moment, right? It's just nice. Every line is parallel. You know, if they're not and they're a cone beam, you can actually reshuffle them from different layers, right? Take different angles from different rotations. You can reshuffle them and make a parallel set. That's one way to handle it. Or you just rewrite the lines. We like the parallel ones because you only have to define one line. But technically speaking, with a cone, you'll get a line that's parameterized by theta instead of constant for theta. Not that big of a deal. Anyway, this is the center point along my detector. And I've got a source and it projects down. And you can see, here's your cross section. This is how much was absorbed. So maybe there was a little more stuff absorbing here and a little bit less on the side because it just went through a thin bit of skin, right? So essentially those rays come down and they drop off their energy, and this is basically how much was the attenuation, i.e. the density and atomic number combination summed up over that length. Does that make sense, what it's doing? So I'm basically just summing up along these lines. And that gives me this number. And this number tells me roughly about how much stuff you went through. This is just here as an example, a simpler example to kind of see that thing. If it was a circle, right? It's like this, imagine this ball, everything had to stay in the column, but when it hit here, they all kind of flattened out. So the thickness here goes there, right? The whole line thickness is here. And take any cut through this side, and that's how tall this is. Right? So it's kind of like that's made a soft Play-Doh and it just goes boop. Right? But that's what the projection is. So you can kind of see, oh yeah, right? It goes from thickness, you know, of 1 or 2, whatever you consider the thickness of that circle, down to 0, and you can kind of see that shape, which looks like, you know, 2 times cosine, right? Good? All right. So what we're going to want to do is to undo this. The most natural thing to do is to just, I took it by smearing it down, I'm going to smear it back the other way. Right? So let's just consider that possibility. Right? I've got this shape in the upper corner. Again, this is from the book. Right? This is the sinogram. So the sinogram, every row happens at a particular angle. So, you know, this is angle 0 down here. At the top, it's at angle pi, right, 180 degrees. So this is the measurement if you read just along the line. Don't go up there, just literally one line thickness. That's going to give you the numbers that correspond to that profile we saw before. How high was the profile? So if it's brighter, it means there was more stuff there. If it's darker, less stuff. Make sense? And so we just do that for a whole bunch of angles, and you get this kind of pattern. And since it's rotating, it looks like a sinusoid going through. Yay! So that's the first part, right? Took all those sinogram images. If I took one particular angle and I smeared it back, this is what you get. And if I did that for all the angles and added them together, and then normalized them so the highest value is 1, this is what you would see. It does indeed, that back smear. So this is just called back projection. There's not just filtered back projection, there's back projection. Back projection was the original idea. And everybody looked at this, and they said, I can see the object, it does really kind of work, but there's all this extra pretty uniform stuff. And you can get a pretty good idea, right? I smeared it back. I did that from all directions. Well, that smear means I basically did a really low frequency value all the way across. And then I count on the overlaps to get to these peaks. But I still added the smear that was never there in the first place. So I added a bunch of low frequency junk. And indeed, this is a constant low frequency haze. So everybody goes, well, I can tell immediately that this is a good idea. I just need to filter it. And I need to filter it in particular some high pass filter. Because I know I'm adding low frequency noise. We got to figure out what's the high pass filter exactly. We've got to figure out some other stuff to it, but we know the idea looks good. Does that make sense? Okay. Don't worry, we got 2 days for this. We're going to build code. I deliberately did not give you this particular PowerPoint because I want you to write code. And if I gave you this, you could just skip to the end and just grab the code on the last PowerPoint. So I'll give you the PowerPoints after next time when we're done. But right now, launch MATLAB and start writing your own code. This will be tremendously useful to you. Right? I know all of you have written MATLAB code before, but you probably haven't written something this big. And if I just asked you, hey, write me filtered back projection, even having heard the ideas, I guarantee you wouldn't be able to just sit down and do it. Right? I'm going to walk you through how you could figure it out. Right? That process is going to be more important than the filtered back projection filter. Right? I want you to be able to look at, because what I'm going to do is basically take you from what would be, you would read in an article, to turn article in, bad academies into functional code. And when you're out on the job, all you're going to have is these academic articles out there published in IEEE. And they force us to write those things as small as possible. And in order to fit their page limits, we have to throw out description so that we can at least get the pure facts into there. And what you get is a very terse description. That's awesome. On the negative side, there's no explanation. So people are like, I don't know how to do that, right? So hopefully at the end of this, you will have a method for how you can turn papers into articles, right? So what I start off with is, I know I want to do something, filtering back projection. So I function to n, all right, that's what I want back, equals filtered back projection. I'm going to pass it a sinogram. I need to know what angles it's at. I know that information ahead of time. Every single piece of code you're going to write is going to have 3 blocks to it whenever you write a function. It's going to have a setup section. It's going to have the execute, the main algorithm itself. And then it's going to have a cleanup. Fix all the weird stuff you did and make it right. Right? Those 3 portions are defined. If you take a CS course, they will tell you the same exact thing. Right? No matter what it is, those 3 sections exist. And so if you break things into those parts, and I suggest breaking your comments into these parts, it'll help. Then I put in advance, not thinking about what I know. I deliberately didn't write every comment I wanted. But I wrote down what you could know at this point from what we've talked about methodology-wise. Right? On the setup, I get a sinogram of theta, but I don't know what the image is. So how big is the image? I'm going to have to figure out the image size. Right? I could get junk data. That's always a safe thing to assume. Somebody gives you bad data, what do I need to check? Right? I'm probably going to have to set up some internal variables. We know we're doing some type of a sum, so I'm going to have to initialize the sum, stuff like that. So I got to set up some data. I know I have to filter. I have to figure out what that filter is and write it. That's all setup things. Once I have all that, we know we're walking through for each angle and doing something. And that something involves, we're going to filter the data in advance because it doesn't, these are all linear operations, summations and filters, right? These are linear, so it doesn't matter the order I do them in. But if I do the filter first, it's a 1-dimensional operation. If I do it after, it's a 2-dimensional operation. And 1-dimensional is faster than 2. So I'm doing the filter first because it's just faster to do the filter first. That's something you could definitely know in advance as well, right? Better to do a 1-dimensional than a 2-dimensional for the same effect. So I'm going to filter my data. I will have known what the filter is of that. I'm going to have to figure out what the projection line is based on my sinogram and that theta. And then I'm gonna have to back project. But that back project is along lines on the detectors. Between them, I like to interpolate. So it's smoother. So that's why I say back project with interpolation, because I back project along lines, and between the lines, I'm gonna interpolate. And MATLAB has functions to do that for me, so yay. All right, and they'll have to clean up. Depends on what mess I make. All right? Does that make sense? That's a basic sequence. We could say that's the type of stuff that has to happen. Once I've got this, I can start filling these in whatever order I figure them out. All right? So this is why I say this would be a good way to set up comments. Most people write their code however jumbled they can think of it, and then go back and try to add comments. I'm suggesting make the comments your helpers. Put in the notes, this is the crud I gotta do, and then you can place things in the right location, and you'll get the final documentation for free. Plus it helps you along the way. Okay, we good? Okay, so we're gonna try to fill in this module over the rest of the PowerPoints. Okay, so first off, one thing I can always do is, just as a good thing, just figure out how big is my sine wave. All right? This is one of my favorite things. Somebody passes me a variable, I want to know how big it is. So I know from the way MATLAB does theirs, remember I told you it's always angles and projections? Yeah, except for MATLAB. Remember I told you that there's that weird flip thing that goes on sometimes? That weird flip thing is MATLAB. I do not know why MATLAB does it this way, but projections are the rows and angles are the columns. Thank you, MATLAB. Right? So that's the way they generate their sine wave. So that's the way I'm calculating. So that's just going to tell me how big it is. But remember, that's kind of projections tells me how wide the detector was, and the angles will tell me, you know, this was the value, the data I took for each of these different angles, and theta will tell me what those angles are. I want to figure out the image size. Let's just assume for the moment it's going to be a square image, n by n. Pretty standard assumption. Yeah. So the question is, what should n be? Now, what would be some reasonable things to try to do to assume for your image size?
Projection length times 2.
Okay, so it should be something proportional to those detectors, right? You know, the image can't be bigger than the detectors, otherwise you'd be missing stuff, right? So it's the image in whatever direction you take it, the image in that dimension has to be smaller, right? It doesn't have to be a lot smaller, so let's assume it's the biggest one that will still fit for it. Is that fair? And then on top of it, I'd really like it to be even. Doesn't have to be, but I'm going to just add that extra little request. Can we have that n is also forced to be even? So how would I go about doing that?
Well, you're in projection variable already, so you can, if you want to make sure that when you're at a 45-degree angle, all of it still fits, you probably have to divide by that.
So this is, I agree, I like your 45-degree thing because you've got it. My one suggestion would be draw a picture, right? Which helps if I have a pen. There we go. All right. I want it n by n, and you are correct. My worst case scenario is my detectors are over here on a 45. Right? So I want to make this so here's my n, and this length here is whatever those projections is. I'm just going to abbreviate projections as P, because I'm lazy. All right? How can I tell n knowing P? Should be pretty straightforward, right? So do it for me. Now, I also add that extra little thing in though, and then once you have that in, figure out how to force it to be even. Cool? Give it a shot before I give you my answer. When you're done, just give me a hand flick or something so I can get down. You done?
I'm kind of cheating though. Like I already had
Some of the code.
from image processing.
Yeah, so try not to, I know that it's there and we did some of this here, but I'm trying to go into more explanation here. Because again, the point is not the code.
Well, like my final project in my class was.
Oh, so then you really don't work.
Yeah.
So, everybody have something? Okay, well, I add myself some extra comments there. All right, so if you did the projection divided by square root of 2, that just gets you the size that fits this. Right? 2 over 2 is what, the 2 times and the 2 times on the bottom. That's just a 1. That washes out. Delta the fact I've added that floor in to get rid of any noise. That's what's going to force it to become even. Because then it could be even or odd after that floor is done, but after I multiply by 2, it's got to be even. All right? So that's just a trick. And it's not doing anything more than that because the 2 and 2 inside is the only change. All right? I've often said most tricks come down to multiply by 1 or add 0. This is make it even by multiplying by 1. Just a clever multiplied by 1. Good? Okay. So let's talk a little bit quick about what's going on when we do this, because this is going to help us to understand the filter. So we're taking some object, take a projection at that angle. All right? Anybody remember what this part right here is called? Central slice theorem. So at that particular angle, this profile, if I take its Fourier transform of this, it will be the exact same as the original object, taking its 2D FFT, and I took a slice at that exact same angle through the origin. That value of the FFT is the FFT of this slice, or this projection. Right? That's kind of neat. I'd really like to just have the FFT. That'd be awesome. So what I can do is by taking all projections from different angles, I'm in essence sampling FFT space. Right? That's really what we're trying to do here. Now, a lot of people will tell you that this is perfect reconstruction. Is it perfect? No, it is not perfect, right? It's going to be darn, if you could sample infinitely, it would be quote unquote perfect, but you can't, so you're not going to sample everything. But it is good, and you can understand it. But let me first give you one thing. When I was looking for a good picture for this, one of the pictures that popped up was Bob. So if anybody ever had Bob Marks here in the department?
He's my advisor.
Oh, is he? Awesome. Yeah, Bob's awesome guy. He's a good friend. But his picture showed up for the slice there when I was looking for pictures, and you can see that same one I've drawn, and he's got that back and forth here, right? So I saw that like I gotta include Bob. There's really nothing I wanted in that, just I thought it was fun. Okay, here's the real part. right? You look at what we've got with this polar grid, right? And you can see we're sampling, like each of those dots, think of it as one of the bins along the projection, right? And we're gonna take that and we're in essence trying to resample it back into a square grid. But it's not exactly right. There's gonna be an effect. Notice in particular how dense it is. And think, so I've just taken that, I've blown it up here, and then I put these circles around it just to help you see, right? This is low frequency, your mid frequencies, there's high frequency as I'm moving out. But I'm sampling the spaces. Let me ask you a question. What do you think the effect of that sampling is? If I'm sampling a whole lot more here than here, and how much more?
You're in this high frequency components.
I am. Is it possible by sampling more that I could also amplify things?
Yeah, I would get like super foggy, kind of.
It will, because the more samples I take, when I carry them over, it's going to weight them according to this. So the question is, what is the density of sampling here versus here? And just consider along any of these particular lines. How many points along this circle? As any other circle, right? So that's telling you as it comes in, what's the angular distance between them? How's it changing?
Angular distance is the same.
Right? So the length, right? Angular distance is the same, but how about the sampling distance now?
Linearly going down.
It's going down linearly. It's going down linearly with the circumference, which means it's going linear down with the radius, which means it's going linear down with frequency. So in essence, what we have done by this, the effect of sampling, is we've in essence multiplied things by 1 over the frequency. So the low frequencies, that's going to be a huge gain. That's why the fog is there. So just by looking at the sampling points and considering those circles, we can get the exact distortion to the filter. Right? So what filter do I have to apply to undo that?
Frequency.
Multiply by frequency. Done. Right? See how clear and easy it is? All right. So, a ramp. Right? I want you to write me now a ramp.
Right, time is it?
We're going to do this one in frequency.
Cool.
So frequency, but you have to figure out how big it is. And I do want it to follow the ramp as close as I can, remembering where the angle goes. So where are the frequency ranges in MATLAB? Is it symmetric about the origin? Where does MATLAB put its frequency range?
Before you do the shift, it's origins on one side.
Yeah, we're not going to bother to shift. We're going to do it natively.
Yeah, origins on one side.
Yeah, origin will be on the left, and it's going to go 0. High frequency will be in the middle, and it'll go back down to the low frequency, but it's open on that side. It's closed on the left. So the 0 point is only on the left of your one. So when you're designing your ramp, the 0 value should only be the first element in your array. It should get to the highest in the middle, and it should come down, and the 2 element, the first one after the center, should be the same as your last element. Right? And it will vary by whether it's even or odd. Right? So we're at the end of our time. So what I would like you to do, and we'll pick up with this next time at what's the answer, write your filter. I want 1 for evens, 1 for odds, so it's exact. And go through. Good?
Do you know the scale of the ramp yet? Why?
Make the highest value 1.
Okay.
Cool deal. Thank you all. We'll pick up there. This should be extremely easy for you.
Yeah.
What I would encourage you to do on it to make it actually somewhat useful to you is think about how you might do it along the curve paths.
right? Because otherwise you're not gonna have anything to think over. And that's more than anything, you wanna have something to think over. I don't care whether you write it up or not, that's your call. But think about how would I go about putting this instead of on straight lines, how would I put it to a curved path instead? Does that make sense?
Yeah, like projections.
Yeah, you know,
Yeah.
the next step we're gonna do is we have to figure out the X and Y line, right? So we got the X goes plus Y
Yeah.
sign, Y minus Z. We're gonna do that part and have you project that along the line. In your case, it's curved line, not a straight line. So it's not an orthogonal. And like I said, you don't have to write the code for that, but just to keep it kind of interesting for you, think how would you do it?
Yeah. Well,
Because otherwise you'll look at this and you're like, hey, I don't know the answer.
well, for the code I have, it's for, it wasn't actually for my final project, it was for one of the other reports. But I included, I took the filter and then I added in like the other ones. Like the chef plugin.
Yeah,
And
all of
stuff like that.
Yeah, that was what we need last time. I'm just saying for right now, if you don't do something that forces your mind to think about it, it just, the effect of thinking over how would I analyze a new problem isn't there.
Yeah, essentially just like,
I'm just saying that'll keep you, yeah, it's a way to think, hey, how would I alter this? Right? Yeah. I mean, you could do a different thing if you want, I'm just suggesting that as something to at least keep your mind engaged. Because when you've done something that's in this direction, otherwise it'll just bore you and you'll get no benefits.
Yeah.
And I hate no
are
benefit.
we also going to do art like this?
So my plan is to do GIF and SAP, so we'll do the parallel versions.
Okay, cause I was just looking at the CT homework and I was like, oh, all I need is art in this, which,
Well, I just put art generically.
okay, but,
Different years I emphasize one or the other, sometimes SAP, sometimes GIF. 1 year I did both and we compared them.
interesting.
You know, so there's a couple different variants. There's really no alternative. And so there are some people who have never seen FPP, so I have to at least do FPP. But I usually don't do art here because I can do one of the other ones and people can extend to art if they want.
Yeah.
And people who did art in the image class aren't bored.
Actually, I have another question.
Sure.
It pertains to my research.